Okay, greetings. So, welcome to today's class. A quick recap, what we were doing yesterday was to consider the forces that were acting on the vehicle. We looked at the physics behind these various force terms, and we essentially wrote down the governing equations, and the place where we stopped was to get the expressions for the loads on the front wheels and the rear wheels respectively. Okay, so this is where we stop. So let us continue from here. So if you look at these two expressions, if we look at the first term on the right hand side of these two expressions, we can immediately observe that these indicate the static load on the front and the rear wheel respectively. That is, let us say the vehicle is standing what to say, on a flat road, right, at rest, then WL2 by L and WL1 by L will be the static load distribution between the front and the rear respectively, right. So that is how we get the longitudinal location of the center of mass also. Okay. So we can immediately observe that the first term on the right hand side of both equations indicate the static load. Okay. So just to highlight that further. So suppose let us say now we consider this stationary car, just drawing a simple schematic. Okay. So this car, okay. So let us say W is, of course this is the forward, this is the direction of motion, right. So let us say this is the front WF and this is the rear WR, and this is L1 and this is L2, right, and the total distance is capital L, which is the wheelbase. Then we can immediately see that WL2 by L will be the load on the front, WL1 by L will be the load on the rear, right. So that is why the first term on the right hand side of the expressions that we derived indicate the static load on the front and the rear wheel respectively. Okay. Now what is the second term? So we can see that the magnitude of the second term is the same. It is H by L times F minus the rolling resistance. But what can we observe? That term is being subtracted from the load on the front wheel and added to the load on the rear wheel, and that is what we can physically observe, right. Let us say we are sitting in a vehicle and the vehicle suddenly starts to accelerate. What happens to all of us? All of us tend to go backward. So the second term indicates what is the so called dynamic longitudinal load transfer that happens due to acceleration. Okay. So this is the indicative of the dynamic load transfer along the longitudinal direction. Okay. So during acceleration, this load transfer happens from the front to the rear. So that is why we see that a quantity is subtracted from WF and the same quantity is added to WR. Okay. So that is the second term on the right hand side of both equations. So we can see that the expression for WF consists of two components, the static load and the dynamic load transfer. So now what we are going to do is to essentially determine what will be the maximum tractive effort that is possible when we drive the front wheels and the rear wheels. Okay. So typically if you look at most vehicles, either the front wheels or the rear wheels are driven. Some vehicles, all the wheels are driven. Okay. So let us look at front wheel drive and rear wheel drives. Okay. So for a front wheel drive, like in most passenger cars today, the maximum tractive effort. Please note that the from yesterday's free body diagram, like the tractive effort at the front was called as FF, tractive effort at the rear was called as FR. For a front wheel drive, FR is 0, okay. So only the front wheels are driven. So the maximum tractive effort is given by, so let us say we call the maximum tractive effort as F max, that is going to be mu p times WF. So what is this mu p? Okay, we will discuss this in more detail when we go to braking, but right now this is the peak or maximum coefficient of friction, like or traction or adhesion at the tire rod interface. So this is a simple way of expressing the maximum traction available at a particular tire rod interface. What we do is that we take a parameter mu, okay, and multiply it by the load on that particular tire, the normal load at the particular tire rod interface, okay. So this coefficient mu is called as the friction coefficient or the traction coefficient or the adhesion coefficient at a particular tire rod interface, okay. So I have put the subscript p to indicate that there is a peak value, okay. So this mu p is the maximum value that you can get at a particular tire rod interface. The value of mu p changes with the type of road surface. Suppose let us say we have a dry asphalt concrete road surface, the value of mu p would be pretty high, but that would decrease as soon as let us say it rains, okay, and the same asphalt concrete road surface becomes wet, due to the rains, the value of mu p will drop, and let us say if it snows, it will drop further. If the snow freezes as ice, it will drop even further. So typically depending on the road surface conditions and the tire conditions and the condition at the interface, this value of mu would change. Not only that, this value of mu also changes with what is called as a wheel slip ratio, which we will come to when we are dealing with braking and anti-lock brake systems. Okay, so right now we will just take it that given the load at a particular tire rod interface, the normal load, the maximum tractive effort that one could expect is the maximum traction coefficient or friction coefficient multiplied by the corresponding load. So that is what we are going to take. So if for a front wheel drive, since only the front wheels are driven, so we are taking F max to be mu p times WF, okay, where WF is the normal load on the front wheels. So now what we do is that we just go and substitute for WF. So that is going to be WL2 by L minus H by L multiplied by F minus RR, but now F will become F max, right, because we are dealing with the limiting maximum force that is available, right. So we are just going to get F max here. So from this expression we can immediately observe that there is F max on both sides. So just simplifying this expression, we will get L times F max is going to be equal to mu p W times L2 minus H times minus mu p H times F max, and this rolling resistance, as we recall, we are going to write it as Fr times W. So this will give us plus mu p H Fr times W, right. So this is what we will get, okay. So if I simplify for F max, we can immediately observe that this expression reduces to mu p W times L2 plus FRH divided by L plus mu p h. So, this is what we will get for the maximum traction that is available for a front wheel drive. Okay. So, this is the expression for F max for a front wheel drive. Let us do a similar exercise for a rear wheel drive, and then like we will compare them. So, similarly for a rear wheel drive, what we are going to abbreviate as RWD, the maximum tractive effort is given by the following. So, F max now is going to be equal to mu p, which is the peak friction coefficient or traction coefficient, times WR. So, let us go back and substitute for WR. So, what is WR? If you recall, it is going to be WL1 by L plus H by L times F max minus RR, right. So, this is going to be WL1 by capital L plus H by L times F max minus RR. So, we do the same simplifications here. So, RR is going to be written as FR times W. So, what we will have is L times F max will be equal to mu p W L1 plus mu p H F max minus mu p H FR W. So, if we simplify this expression, we will get F max to be equal to mu p W times L1 minus FRH divided by L minus mu p H. So, this is the maximum tractive force for a rear wheel drive. This is the maximum tractive force for a front wheel drive. Okay. So, now we can immediately observe the following. So, having obtained what is the maximum limit of traction, like that is possible for a given set of wheels, okay, either the front wheels or the rear wheels. Obviously, like we would want to drive the wheels where the maximum capacity is available, right. So, how do we make a choice between a front wheel drive and a rear wheel drive? So, now for the sake of comparison, let us first consider the denominator term of the two expressions, right, for the front wheel drive and the rear wheel drive. So, the term in the denominator of the front wheel drive F max is L plus mu p h, okay. The term in the denominator of the rear wheel drive F max is L minus mu p h. So, which do you think is smaller, L minus mu p h, right. So, the reciprocal is going to be greater in the expression for the rear wheel drive. Now, why are we getting this effect? Because of dynamic load transfer. See, from where did this mu p h come? It came from here, right. When we substituted for F max as mu p times W, like we essentially had that mu p h and minus mu p h appearing in the denominator for the two drive configurations, right. So, the dynamic load transfer during acceleration seems to be increasing the maximum tractive capacity available at the rear wheels. If you compare only the denominator term, okay, we are going one by one, okay. So, that is the first observation. Now, let us look at the numerator. Mu p times W is the same, right. However, we have L2 plus FRH and L1 minus FRH. For the time being, for the sake of argument, let us neglect FRH, okay, Fr times H is going to be smaller when compared to L1 and L2. For the sake of argument, let us neglect it. Well, doing calculations we will include them, just for the qualitative what to say a comparison, let us neglect the term FRH and plus or minus FRH in the two expressions. So, the front wheel drive expression has L2 in the numerator and the rear wheel drive expression has L1 in the numerator, right, mu p w being common. So, let us take a typical passenger car that we see on the road. We all of us have observed that it is a front wheel drive vehicle, irrespective of the fact that the dynamic load transfer takes place from front to rear during acceleration. As a result, having that L minus mu p h in the denominator would have helped, but still we go for a front wheel drive. What do you think is the reason? Because it is due to the way in which mass is distributed, right, in the vehicle. So, if you look at a typical passenger car, the engine, the transmission and almost all other components are towards the front. Okay. So, what is going to happen is that the center of mass of the vehicle or center of gravity is going to be shifted to the front. So, if the center of gravity is shifted to the front, which value is going to be higher, L2 or L1? L2, right. So, obviously we can observe that despite the fact that dynamic load transfer is going to transfer the load from front to rear, the fact that L2 is higher still makes it advantageous to drive the front wheels, right. So, that is an observation we could make. And please remember, this amount of dynamic load transfer also depends on H in addition to mu p, right, if you look at denominator. So, the lower the value of H, like the lower is going to be the effect, okay, of dynamic load transfer. So, that is something which we need to observe also, okay. So, on the other hand, let us say we take a bus or a truck or a lorry, right. What happens in a truck? Let us say we drive the rear wheels. So, in a truck, in a typical truck, even though the engine is in the front typically, right, there is a propeller shaft which takes the output from the transmission all the way along the length of the vehicle and drives the rear wheels. Why would we do that? Because of course, we are going to get an advantage due to dynamic load transfer if we drive the rear wheel. However, in a truck, the main load comes from the goods or the material that the truck will carry, and where is it carried? It is shifted towards the rear. So, you will see that for a fully laden truck, right, the CG is going to be shifted to the rear. So, which value will be higher? L1, and where does L1 appear? In the expression for the rear wheel drive. So, it makes more sense to drive the rear wheels because of this fact, and also like dynamic load transfer also helps. Of course, the actual capacity of the powertrain is different, okay. This is from the perspective of the vehicle's dynamic response, right. So, that is these two expressions gives us what is the capability or capacity available at the front and the rear wheels, and this sort of analysis becomes very important, particularly when we go for high performance vehicles. That is, let us say you go for high performance vehicle, let us say even we take a race car. What happens in a race car? Typically we want to put the engine, powertrain, everything closer to the rear, and we drive the rear wheels, right, and even the driver is shifted to the rear due to various reasons. But from this perspective, what happens? Although H is very small, right, the value of L1 will be larger. So, we drive the rear wheels because we want to have faster acceleration, higher acceleration. If you want to have higher acceleration, yes, my engine transmission should develop that force or torque, that thrust, but the tire rod interface should also be able to sustain that force, and that is what this expression gives me, right. This gives us what is the capacity at a particular tire rod interface, either at the front or the rear wheels. So, using this we can get a rough idea as to why the drive and the powertrain are realized the way they are, right, for different class of vehicles.